Welcome to the third module or third lecture, whatever you want to call it. So, we are going to talk about sequences. Sequences are nothing but looking at counting as a function. So, I had said that counting our set is same as putting it in one-to-one correspondence with a set of natural numbers. So, a set is countable if either it is finite or I can do this correspondence. So, now let me consider a function which is same as counting, but I am trying to map the set of natural numbers to the set R of real numbers. So, this map which takes an element n and maps it to a real number x n, and if I list down all the, for every n, if I list down exhaustively the outputs that I get, then that exhaustive list is called a sequence. A sequence of course is not representing the range of the function. For example, if I have this function f n equal to 1 by n, then what I get is a sequence of this form. I start with n equal to 1, n equal to 2 and go on. So, it is 1 half, 1 by 3, 1 by 4 and so on and so forth. Of course, you could have a sequence which is slightly more interesting looking, minus 1 to the power n, which would just go on having this, but you just have to list down everything. So, that forms a sequence. If you look at the range of this function minus 1 by n, this is just minus 1 plus 1. If you look at the way the values are moving in this particular sequence, 1 half, 1/3, 1/4 is decreasing and going towards 0. So, then we can say that this whole sequence values are moving towards 0. This process of moving towards a particular value or a limit is called the notion of a convergence of a sequence, and this one just does not converge. The values move around 2 points, minus 1 plus 1, minus 1 plus 1. So, this is an oscillatory sequence, a sequence whose values do not blow up or they do not go to a limit, but move between two values. So, another type of sequence, for example, so it is just the same repetition. So, here I can make the numbers as big as I like. So, you do not go to a fixed towards a fixed number. So, this is called a divergent sequence. So, this sequence is called convergent, this sequence is called oscillatory, and the third one is called divergent. So, now what we intend to do is the following. We want to talk about what is the meaning of convergence. What is the meaning of a sequence x n moving towards a number L. So, when I was a youngster and was in my high school, so one of our physics teachers started talking about derivatives and all those things, limits and everything, and we were not understanding, being students of class 11. So, we asked him what is the meaning of a limit. So, he said that limit means coming, but still not coming, which is essentially the fact, but which can be cloaked in a much more intelligent language. X n goes to L means that as I make n as large as possible, the distance between x n and L can be made as small as I like. That is the idea. So, you say, if you tell me, okay, I will give you a distance between x n and L, or I will fix up a number, can you find x n's so that all x n minus L would be less than that epsilon. That is, beyond some finite number of elements of the sequence, will all the x n's be such that the distance would be less than a given epsilon. So, that is the meaning of being able to make the sequence move closer and closer to L. that whatever be your distance, however small, I can make that, I can show that after a finite number of terms, all my sequence terms are getting inside the band xn, the xn would lie between L minus epsilon and L plus epsilon. So, this actually implies, if you say that this is less than epsilon, then it would imply that xn minus L is between plus epsilon and minus epsilon. So, xn is between L plus epsilon and L minus epsilon. So, the idea is that you have to tell me, if I give you an epsilon, you have to tell me what is the finite number of elements that you are leaving off. So, that is the, so determination of that finite number of elements is the main thing. So, given an epsilon, you have to tell, okay, if I throw away this finite number of elements from the sequence, rest are all within this band. So, that distances are all less than epsilon. So, this is cloaked in a much more formal language which we call the epsilon delta formalism, though you need not be too much bothered about it at this stage, but just for the heck of it, I am just writing the definition. So, given epsilon greater than 0, no matter how small, there should exist an n naught, a natural number, such that for all n greater than equal to n naught, I must have this fact true. So, xn going to L simply means that this, that if you give me an epsilon, I should be able to tell you what amount of elements of the sequence I should forget, and remaining every one of them should lie between L plus epsilon and L minus epsilon. So, that is the very basic idea which we can draw out. So, suppose this is n and this is xn, and now we can just talk about, so this is my L which I think the sequence will go to. So, I will take some epsilon and create a 2 epsilon band around L. So, this point is L plus epsilon and this point is L minus epsilon. And now, suppose this is my 1, 2, 3, 4, 5, 6, 7, 8. So, maybe this is here, the second one is here, the third one is there, the fourth one is there, the fifth one is here, the sixth one is here, the seventh one is here, eighth one is here, and so on. So, what I see that, okay, the first one is outside the L epsilon band, this 2 epsilon band, epsilon and epsilon. So, this length is 2 epsilon, 2 epsilon. So, it is outside this 2 epsilon band, right, and so is 2, but 3 is inside, 4 is inside. So, can we say, okay, if we leave out 2 elements, everything is inside? No, we cannot say, because we see that 5 is outside, but after 5 we see that everything remains inside. If it, let us assume that it remains inside, then we can say, if I leave out 5 of them, then for this particular epsilon, all the other terms starting from 6 towards infinity and going on, that would remain in this 2 epsilon band. So, this is the very basic idea of convergence which we have written down in this language. Now, a very important notion is that of a bounded sequence. So, a sequence, I am writing SUQ for short. See, this is the notation of a sequence in short, is bounded if there exists k greater than or equal to 0, such that mod of xn. So, this simply means, so essentially k is the upper bound of the sequence and minus k is the lower bound of the sequence. In fact, you can separate them and say you have a sequence may have an upper bound, but may not have a lower bound, but or may have both the bounds. So, for example, upper bound means there is k element of R such that x n is less than equal to k for all n. So, this is true for all n. Now, you can talk about a lower bound. So, there is q element of R such that q is less than equal to x n for all n. So, these two concepts will become very, very important, but a very important idea in mathematics is the existence of the least upper bound. So, if k is an upper bound, possibly there could not be any other upper bound lesser than k, or there could be an upper bound which is lesser than k. So, finally, we will find an upper bound which is called the least upper bound or the supremum. So, supreme we have to decide the notion of supremum of x n and the greatest lower bound which is called the infimum of x n. So, these are two important quantities. So, if you take a sequence and you say that say 1 is an upper bound to a sequence, then 2 is also an upper bound to the sequence. I will just go back and show you. For example, you take this sequence. So, plus 1 is an upper bound to this sequence, and hence 2 is also an upper bound to this sequence. Everything is bounded by 1. So, 1 is an upper bound to the sequence, minus 1 is a lower bound to the sequence. Then minus 2 is also a lower bound to the sequence, but plus 1 is the least upper bound in this case. So, because if I consider say anything less than 1, it cannot be an upper bound to this, right. So, you have to, you cannot get an element, you should be able to see what happens is that when you have these sequences, so among all the upper bounds means what do I mean by this is a very important concept and has to be kept in mind, and that is very useful in many things including algorithms. See what happens, see you have taken an upper bound here and then you have considered a lower bound here, but among the lower bound there is something called the greatest lower bound, among the upper bound there is something called the least upper bound, means if you drop that number, then that number will not become an upper bound anymore, right. That is the whole idea. That is, if you drop that number by some quantity, that should not remain an upper bound of the sequence. For example, I will tell you, you look at 1 half this sequence. What is an upper bound here? 1 is upper bound here. If you decrease it to say 1 minus epsilon, say if you take any number between 1 and half, you take 3/4. And is it 3/4 an upper bound? No, because the quantity 1 which is an element of that set is bigger than this. So, it cannot be an upper bound, it violates this definition. Similarly, for this case, this sequence, so in this case the supremum of x n of this particular sequence is 1, while the infimum is 0, because you increase any number 0 by any number, I will always find a n such that 1 by n is below that number. So, this is something you have to give a little thought to, because these are very important concepts. So, I will come to now the concepts of increasing and decreasing sequence. Before that, let me tell you that every convergence sequence is bounded. The proof can be done by using the epsilon delta formalism, which I will not get into the details. If I have time, I will tell you a bit, but let me now tell you that every convergence sequence is bounded, but every bounded sequence need not be convergent. For example, the sequence -1 + 1 -1 + 1, it is not convergent, but still it is bounded. So, bounded sequences do not need to be convergent, but convergent sequences need to be bounded. I want to repeat this term as I go on, that you have to you know sequences much better if you know that every bounded sequence need not be convergent. Just like I will tell you that when we will learn about derivatives, you will know calculus much better if you know at the very outset that every continuous function did not have a derivative. So, let us look at something called increasing sequence. You can understand what is the meaning of increasing sequence. Means the terms of the sequence increases as I increase the value of n, that is x of n plus 1 must be bigger than x n. This is what we call increasing sequence. And then something is called the decreasing sequence, that as I increase the value of n, the value of x n decreases. So, what is so fascinating about increasing and decreasing sequences? If I have a sequence which is bounded and increasing, then that sequence must be convergent and will converge to its supremum. And if I have a sequence which is lower bounded and decreasing, then it will converge to its infimum. So, if I have a sequence which is increasing and has an upper bound, it will converge to its supremum. So, here I am giving that if I have a bounded sequence, which you know that bounded sequence need not be convergent, but if it is additionally having the feature that it is increasing or decreasing, then it is convergent. So, here we are adding some conditions on a bounded sequence to show that when a bounded sequence can be convergent. So, if x n is increasing and bounded above, then x n converges to the supremum or the least upper bound, then x n converges to its supremum. So, the idea, so please look at the supremum and infimum idea very well. We have already mentioned a text, and I think you should look into the idea of supremum and infimum very well, because we are of course doing the things in a very short time. Now, let me explain to you this idea pictorially, and by explaining to this idea pictorially, we will end today's discussion. So, let A be the bound. So, let x n has an upper bound given by A. So, let this be A. So, this is my n, I am plotting the n, and this is I am plotting the value of x n. Now, my function, my thing is increasing. So, this I have assumed as increasing. So, let us see. So, this is say x 1. So, x 2 must be bigger than or equal to x 1. So, say let us take x 2 and x 3 are same. Say then I have x 4, then I have x 5, then I have x 6. So, none of them can exceed a, because every value has to be less than a. So, then I have x 7, then I have x 8. You see, this is almost becoming asymptotical to this line, x 9 and so forth. So, it must converge, it cannot go beyond. So, it asymptotically, if this a is my supremum, it is asymptotically going towards a. So, with this idea, I would like to end today's discussion on sequences. But tomorrow we will, or in the next class, we will concentrate on talking about something called a subsequence. Subsequence, the Bolzano-Weierstrass theorem, and about Cauchy sequences. So, these are very important aspects of calculus, advanced calculus rather. We are not doing high school calculus, just I want to keep in mind this thing. So, I hope you have a very basic idea of what is going on. You have to remember convergent sequences are important. Every bounded sequence is not convergent, but if a sequence is bounded above and is increasing, then it converges to its supremum. If a sequence is bounded below and is decreasing, then it converges to its infimum. Thank you very much for your attention.